So yeah, Spring with Kotlin coroutines, and let's get started. I can skip this. Thank you, Jarno. A little bit, why coroutines, why reactive, why does it matter? So this is a graph of Apache HTTPD. Does that ring a bell for people? The web server. And when you look at the timeline, it's from 1995 to 2005. So it's a while ago, right? And the blue line that's going up and up and up, that's Apache HTTPD. And I'm not sure about you, but in the projects I do, there's no Apache HTTPD anymore. That's due to multiple, but it's all Nginx, right? So the old HTTPD used to function, when it gets a request, there's one thread assigned to that request, and it starts, getting the bytes and sending it out through a socket to the client. So one thread per request. And basically, at that time, CPUs were less powerful, I guess. But just the sheer switching between the threads meant that the whole server couldn't do any more than 250 requests at a time. And what did Nginx do? It implemented it differently using an event loop. So one thread processing all the requests, and if it couldn't do anything, start working on the different request. And it just important point. So one processing thread per core, and it just blew Apache HTTPD away. I have to say though that they did come up with a different processing model, obviously. So nowadays it also works with an event loop. But the point is that reactive programming is much more performant at scale. So async programming, non-blocking. Why do it? Well, in the user interface, it's clear, right? Whether it's your mobile app or whether it's a browser application, you just need to be asynchronous. But on the server side, it's a different story. And my talk is about programming for the server side. And so the essence is that JVM threads currently are called heavyweight. Anybody an idea what the weight is? How much memory a thread takes? JVM thread. Yeah, exactly. Yeah. So the heavyweight means how much memory it takes, and also the switching between threads, as I mentioned, the context switching. Of course, you can just ask your JVM what memory one thread will take, and also you can change it. So some frameworks have call stacks that are that deep that they need to increase this. So with 1 megabyte per thread, how many threads can you have? Conceivably, 1,000 is fine. 100,000 is not, I don't think. And also, if you have 1,000 threads, then probably your server, it won't be maxed out. The CPU won't be, even though you the performance, how to put it, So let's say you have a high load, and it can't take anymore, and still the CPU is not fully used. So that's low utilization, right? You have these resources, you're paying for them, perhaps in the cloud where they're more expensive, and a big part of your CPU just sits there doing nothing. So that's what reactive programming fixes as well. So some of the use cases where that matters, if you have a lot of devices, small devices working on slow connections, making really long requests, because that means obviously that you'll have at any point in time a lot of requests going on, right? So if your application consists of microservices, if you have one application server and it needs 1 gigabyte for just for the threads, yeah, okay. But if you have for just one application, let's say 30 JVMs, each needing a gig, that is maybe more of a concern. Yeah, so an important, so if you want to use your resources fully and spend less doing the same work. And this is more, apparently from a computer science perspective, the 99th percentile, right? When your system is chugging away under full load, the processing of your requests is much more flat, and you don't have outliers where suddenly the response time explodes, which is nice, right? When you really need it. So if you remember one thing, more throughput with the same resources. So an extra reason I think it's really interesting is that so Spring has had Webflux, of course, and Spring Reactor, but in the latest releases of Spring Framework, Spring Boot, Spring Data, they've really made a big push on reactive programming with coroutines in Kotlin, and I think that's a major factor to study this well and start using it. It's a big vote of confidence, I think, in both Kotlin and reactive programming. So this is in presentation new features for Spring Framework 5.2, and reactive transactions, RSocket, something I won't get into tonight, but that's also strongly, it's a protocol that's strongly related to reactive and stream processing. Kotlin coroutines, Kotlin functions for web MVC. Similarly, in Spring Data, they have R2DBC. I'll go into that in more depth. And then programming APIs that translate what used to be in Spring Reactor to the world of Kotlin coroutines. I'll go into this in more depth as well. So, yeah, what that says to me is that Spring is all in on Kotlin coroutines, and and I'm really enthusiastic about Kotlin, so I hope that's a signal to the community that it's a safe bet and it's really handy. So this is the outline of my talk. First dive into coroutines, the basics. Then spend some time on flows, which is a part of the coroutine toolkit. And then dive into, what does Spring offer in that respect. So briefly, how many people have been working with, let's say, some variation of RX Java or RxJS or... cool. So that's, I'd say 2/3. And yeah, well then I already have my answer. So everybody has some experience with reactive, so that's cool. I'll try to, connect... how to put it, explain stuff in terms of observables as well. Yeah, so let's get started with the basics. Let's just start with some code. This is, coroutines if you're not using any frameworks, right? Just to see them in isolation. we start out in a standard JVM main function, and so that's standard works with JVM threads, right? So you're in the world of heavyweight threads, and first we start a coroutine scope, which brings us in the world of non-blocking lightweight threads, basically coroutines. And given that we now have a coroutine scope, we can start a coroutine, for instance. A little bit of context. A coroutine is a lightweight thread, you could say. But we use the term coroutine because they in turn run on top of threads, so it would be confusing to call them. So if you encounter the word fiber, by the way, for instance, in the context of Project Loom, that's basically the same as a coroutine. So we can start other scopes, and any coroutines that we run within such a scope will have a shared exception handling, and will all end at the end of that scope. So I'm not sure what your experience is in Java applications, but when I'm developing an application, I'm not that eager to start running my own threads. So why is that? Because, yeah, I find it hard to make sure I don't have a memory leak. So even with really stable application frameworks like Spring, you can still have the case where some threads are running longer than expected, and you get these warnings in your application log. Currently, I'm using coroutines in an application in production, and yeah, it just works. So that whole feeling I had about starting your own processing, that apprehension is for me completely gone with coroutines, and that's because of that they are scoped and memory managed. Does that make sense? So at the end of a coroutine scope, they're all completed or ended. And within, when we started a coroutine, we can call suspending functions. So that's the asynchronous form of any method or function. Any point in your code where you call a suspending function is also called a suspension point. I'll get back to that later on. But basically, it's a point where the scheduler is free to do other work. That's called, your coroutine code should definitely call suspending functions, because that will be suspension points. And if there are none, there's a special yield method. But it should suspend somewhere, because otherwise nobody else will get a chance. So a little bit of the word yield. So I'm not a native speaker of Dutch, of English. I'm Dutch, and so to me, so yield is apparently in traffic, giving way to the other. And so when you think about concurrency, yielding also means give other threads a chance. By the way, this apparently is a sign in Alaska. So apparently in Alaska you can have aircrafts crossing the road. So it's I mentioned suspending functions. So this is what it looks like. This is basically the equivalent of thread.sleep, but then the suspending coroutine form of it. And the keyword suspend in front says that it's suspendable, and also that from the implementation of that suspending function, we can only call other suspending functions, and in turn, if code tries to call us, they need to be suspending as well. So so that raises the question: how do you make your application suspending? One side note: it's definitely possible to have your HTTP requests coming in, for instance, in a non-blocking mode, and then you have some legacy API that you need to call, and yeah, it happens to be blocking. That's perfectly possible, but for throughput, it's best if your application is non-blocking end-to-end. And thankfully, with the new releases of the Spring, that's definitely possible. So a little bit, reading the code. It takes a bit of getting used to the suspend keyword in front. That really tells you that this is an asynchronous, non-blocking function or method. So it's basically the equivalent of a function that returns a mono of string or a completable future of string or promise of string in JavaScript terms. But the return value is not wrapped in a container type, and I think that makes all the difference. That makes the programming much more clear and much less boilerplate as far as I'm concerned. Yeah, so I'm all for functional programming, and flat mapping is fine, but it's not a goal in itself. So I think this is really cool. Yeah, so a little bit more about Kotlin function types if you're not using a framework. So yeah, as I mentioned, with coroutines, I don't think you should be afraid of starting your own coroutines within your application, maybe, to do some scheduled processing or stuff like that. The kind of stuff that I'd have the feeling, that my framework needs to support it. And yeah, nowadays you can just run your own coroutine that wakes up every, 5 minutes to do some processing and stuff like that. So to start a coroutine, you have these builder functions, and we'll go through it a little bit. How many people have Kotlin experience? Yeah, okay, so a lot. So, extension functions and functions with receiver type are well known. Well, that makes it easier to read. We fire off a coroutine with this launch method. And to be able to do that, we need to have a coroutine scope. So that's for the memory management, right? So that we definitely have no leaking coroutines. A coroutine runs in the, you start it in a coroutine scope, and a coroutine scope in turn has a coroutine context. And the thing to remember, coroutine context is basically the equivalent of a thread local in JVM threads terms, and we'll get back to that later on. So by default it has an empty one, but you can put more stuff in the context of the coroutine, and we'll give examples of stuff being in the coroutine context. And so this is where you give it your block of code, right? And so what surprised me is that the signature, the type of the function, the suspend keyword is part of the type of the function. So it's not some syntactic stuff it's a different type. This function is a different type than just coroutine scope to unit. And then, yeah, if we fire off a coroutine, yeah, we want to have a handle to it, right? So that we can see, is it still running? We can stop it, etc. So about the coroutine scope, we start coroutines. We need a coroutine scope. So any coroutines we start will be, yeah, children of this of one job in this coroutine scope. So that will help us say, you know, cancel all of them or stuff like that. And as I mentioned, it provides context. So that's the context is the thread local like thing, if that makes sense. Okay, so that's the basics of coroutines and suspendable functions. So a little bit about how they work. So on the top of the screen, we have a few coroutines running, so you can have a lot of them, right? And they are all consist of parts, yeah, basically steps, and the steps are distinguished by suspension points in between. And so beneath the coroutines, we have threads. And so, yeah, the whole point is that we can have a lot of coroutines, but our goal is to only have one thread per core. So that's a really low number, right? And then the coroutines, their steps are interleaved on those threads per core. And they don't need to run on one core, but they do need to be consecutive in the processing. So this interleaving is concurrency. And yeah, so what I said, the point is that you can have a lot of them. So 100,000 coroutines is no problem in your application. That's why we call them lightweight. And as I mentioned, the level underneath is the cores. And so this is how coroutines work. And why you can't assume that the code running, you know, in your suspending function, that it's continuously on the same JVM thread. That all depends on the dispatcher it runs on. So a little bit of lingo. Dispatcher is basically a thread pool, yeah. So a little bit about IDE support. So when you just look at the you know, at coroutine code, you know, let's say printed out on paper or, you know, or in a text editor, you can't immediately tell which functions are suspending, right? So IntelliJ helps you out there. You know, in the left gutter, you see this sign, and that says that's a suspension point. So that's where you're calling a suspending function. So that's one way it helps you out. Oh yeah, and also so in right next to the coroutine scope block, you see that there's a yeah, how to put it, a hint that the this in that block is a coroutine scope. So that's another part that you don't see, right? The this type is generally not printed. That's the whole point of this. So that's another way it helps you understanding code by just reading it. So that's really important, right? So a different way it helps is there's a reactive debugger. And so if you enable stack, yeah, how to put it, that the stack is available here, the asynchronous stack, and there's basically hardly any reason not to enable that. Yeah, then you get meaningful logs in your application log. You know, this is where it failed, instead of some generic it filled in the thread pool, which you otherwise have with asynchronous code. So this is really, and in the debugger you see your asynchronous stack trace, your stack, your call stack. That's really nice, right? So a little bit about sequential and concurrent processing with coroutines. I don't know about your job, but this is, the hello world of the world I live in. You're calling some API where you get some product names, and then you have some other API where you just can get one product at a time. It's a legacy system. It doesn't make sense, but hey, that's how it works. And so how are we calling them sequentially, and how we will call them in parallel? So sequentially, our method get product names is suspending, and get product is suspending, and so that's why our combined method has to be suspending as well. So yeah, that's it. So when you compare that to approaches where you get a promise back or an observable, you need to flat map it, right? And flat mapping is fine, but it's a little bit of boilerplate around the stuff that you want to do, and so that's what I find really powerful. Yeah, so that's it. But so in calling stuff concurrently, what we do is, first, of course, we call asynchronously get product names, and then for everyone, we fire off a coroutine, and we just get a so-called deferred of what it will return. So the async function is basically the equivalent of the launch function, so that's where a coroutine is started. But the difference is you get a handle back to what you can await. So basically, what will be a value, and you don't need to flat map it. You just await it. So the strange thing is, I've been programming in Scala, and there the one thing you should never do is await your future, etc., because that would block the JVM thread. And here we can await because we have plenty of coroutines. So that's fine. Does that make sense? Yeah.
It makes sense, but I'm wondering. I often, or sometimes, run into the case where that list of product names might be like 100.
Mm-hmm.
Get product called as a network call. So now I'm launching 100 concurrent HTTP requests to some service.
Yeah. As I mentioned, this is a bit contrived, right? Because I started out by saying, it's some legacy API and it's suboptimal.
What would be a way to limit the...
Very good question. I have a remark here that, let's see, that this is unbounded concurrency, right? So you don't know how many coroutines it will start, so that's always a sign, let's not do this. They're working on really great concurrent processing, where you can say, just use, do 4 in concurrently or 10 or whatever. But they want to get the API just right, and that hasn't landed yet.
So for now, I usually chunk it, but it's kind of faking it, because like I chunk the list in lists of 5 or something, and then I kick off 10, and then the next 10, and then the next 10. But of course, you get this sawtooth.
Yeah. And there's, I can show you some stuff after the stand-up, after the demo. Yeah. Never long back and forth during the stand-up, right? going back, to be able to fire off these concurrent coroutines, we need to have a coroutine scope, and so we start one just within that will live only within this method. And as I mentioned, all the coroutines you start in that coroutine scope will only live, for the duration of the block, basically. And so this guarantees us that at the end of the method products, they're all finished. So this is, memory management, basically, right? Yeah.
So am I correct in understanding that when you mark a function as suspend, you don't automatically get a coroutine scope within the body of the function? You have to explicitly make one to do this kind of thing?
Yeah, so the question is, in a suspending function, is there already a coroutine scope, or do you need to make one? So that's when you start out with coroutines and suspending functions, a bit getting used to. So at the top level, there has to be a coroutine scope, but in between, you don't have a direct reference to it. But there's the coroutine context, and that hooks whatever you're doing ultimately in the puts it underneath the top coroutine scope. So it's a hierarchy, if that makes sense.
Okay.
So if this function is called from a coroutine scope, you do have a coroutine scope in the first line. You just add you nest another one here.
So the question is, can you repeat it?
Well, it's not really a question. I was trying to clarify, but maybe it doesn't help. So if you imagine this function being called from another place where there is already a coroutine scope,
Yeah.
then this code is executed in coroutine scope.
Oh yeah, no, absolutely. Thank you. It's definitely the case that if you're in a suspending function, when you go up the call stack, at some point there has to be a coroutine scope because you're running by definition in a coroutine. Yeah.
So, but in this specific example, if you were to remove the coroutine scope wrapping and just do port names of map and an async and await, would that also work?
No. So, yeah, and so that's the first thing you note. So the question is, if we would remove the coroutine scope and just leave the rest of the code, would that work? That won't compile, because the async function, just like the launch function, is an extension function on coroutine scope. So it won't compile.
Okay.
And I'm glad, because it
Will compile if it is called from another coroutine.
Yeah, well, let's get into it after, if you don't mind. I have some more slides to handle. So this is parallel processing, concurrent processing, and we just await. So there are several suspension points in this whole suspend function products. So that's the point where other coroutines can have their turn on the dispatcher, right? So it's cooperative parallelism and not preemptive. So these are all suspension points, or suspend functions that we're calling. Okay, so that was coroutines and suspending functions, and but there's also flows. So the terminology, there's also flow in the JDK, right, from Java 9. So that's basically the interoperability standard of reactive streams. And so the flow of coroutines has some stuff there in common with it, but this is Kotlin's flow. So a flow, this is, let's start with some code. So this is a flow of ints, and first we emit 1, then we emit 2, and then we throw an exception. So that feels really like observables, right? So that it's very close to it, but it's also different in some points. So a flow is basically, yeah, this is some, a bit regular expression like, so it's 0 or multiple values, ended possibly by completion or an exception. So this is all the, but so one key point is that a flow can be never ending, right? The completion can never happen, and if the exception doesn't happen either, it goes on and on. So before I'd like to approach flows via sequences. Has anybody worked with sequences in Kotlin? Yeah? Okay, well, I'll explain them. So this is a sequence of our famous friend Fibonacci, right? That's always in streams. So basically we start out with Fibonacci, right? That's 1, 1, 2, 5, 8, etc. Yeah. So we start out with our initial term, and then we yield, we produce values every time, and then combining the results afterwards. So the sequence is endless. So when I first saw this kind of code first, I felt, while true, that doesn't feel right, but it's suspending in between, and there's no problem. It is a var, a variable. So yeah, this is imperative code, right? So I'm coming from Scala, functional programming. So that's bad, right? That's what you learn. But yeah, it's running within one coroutine basically. So yeah, why is it bad to update a var from So there are alternatives, by the way. But so the key point is a sequence is like an iterator. So you can have, let's say, an iterator of random values, or so it's never ending. And the difference is an iterator, I call the iterator and I get a new value. But with a sequence, it's the reverse. The sequence produces new values. And if I map it, let's say, that's called when it happens. So that's a major difference. And we can map and flat map it. So it's like an iterator, endless, possibly endless, but the interaction direction is the reverse. Something else it has in common with, so sequence is basically, another way of looking at the sequence is that it's a lazy collection. So, you only when you access a next value, it's created. When you look at sequences, it's, let's say, well, if you've worked with observables, this will be familiar. Somewhere you're doing some heavy work, right? You're making a remote call, or you're processing some stuff, and the question with these things is, when does that happen? So in this code, the terminal operation, so for each is the terminal operation. That's the part where the work is really being done. So before we call the terminal operation, the value sequence, seek, is just a machine that we're not running yet, machine for values. So if you've worked with RxJS or the modern Angular, it's the famous issue of why is my server being called twice? If that doesn't sounds familiar. So that's the same kind of thing. if you want to impress your colleagues, you call that where that's where the computation materializes. That sounds very so that's a very computer science. So this is all to say that if we the sequence in itself is cold. Cold and hot is terminology from RX. But that's basically what it means. So a little bit about terminal operations and intermediate operations. So map, for instance, is an intermediate operation. You know, to be, and that means that at the point of map itself, there's nothing where you call it initially. Nothing is being done yet. And yeah, intuitively, you know, if for map it only needs to look at one value, right? Not at all the values. So that's a distinction I make for myself. So filter is the same, of course. Distinct, you can just group. You don't have to look at all values to produce the distinct values. It will be stateful though. But for instance, count is definitely terminal because you have to have all the values, right? So that's where the work is really being done. And yeah, for each can't be anything but a terminal operation, right? Because it doesn't produce values. It's so that's where the side effects happen. And yeah, all by definition you need to know all the values. So this distinction of intermediate methods and terminal methods is really important. By the way, I showed you an imperative version of Fibonacci. Of course, there's a way of doing it in the functional way. So you basically have a builder here that you, it's basically the reverse of a fold, this function. Yeah, so why did I start, you know, I said this part is about flows and then I started talking about sequence. Well, it's basically because flows are very much like sequences. So they're lazy, they're cold, but the difference is, that's an important point. So within a flow, you can call suspending functions. So suspending functions are basically what combines coroutines and flows. And this is the equivalent of a yield in a sequence. By the way, back pressure, does that sound familiar? Yeah, you don't want to overwhelm your consumers, right? So basically, yeah, that's because the processing suspends, you get, yeah, the implementation of back pressure is basically, yeah, standard, no extra work. So remember when I mentioned, you know, where is the work being done? So here it's the, here it's the intermediate is the map. So here nothing, you know, no heavy work is being done yet, and this is where the flow, yeah, materializes or where it does the work by default. But the difference is this is asynchronous. And when I go back, so at the second collect, by default the work would be done again. I have to note though that not all flows are can be run twice. So that differs per implementation. So they're both cold and lazy, but flows are non-blocking, and yeah, they're really easy to use for streaming results, and so that we'll see in the Spring code. So a flow in Kotlin is approximately the same as a flux in Reactor, is approximately and those implement the reactive streams standard, right? So reactive Spring, what do we need to make an application end-to-end reactive? Well, the incoming stuff, which is often HTTP, right? The outgoing stuff, we're calling other services. We store some data, either NoSQL or, of course, relational databases. So those are major parts for making an end-to-end non-blocking application. But yeah, I think I mentioned it in the beginning. There's some stuff that really assumes threads, right, in the JVM world. So that's transactions, that's security, that's tracing, for instance. So I'll go into that, how that works in a reactive world. So this is basically the stuff that happens in your thread local, right? So this is an HTTP endpoint in Spring Flux, Web Flux. So this is a builder function for an HTTP API. So what we see is, we see the path, we see the HTTP method, and then it's basically mapped to a function that does the real work. A get at the root will give a view of users, and a get on /API/user will give a JSON response, for instance. The methods that it's mapped on are suspending, of course, right? Because it needs to be non-blocking. And those functions are functions from server request to server response, which makes sense because that's what an HTTP endpoint is. And personally, I find this rather elegant. No annotations, by the way. So this also, these router functions, you can combine them using combining functions like OR and AND. So here, for instance, it's, if you do, you send a request /API user or /users, in both cases will invoke the same method. And similarly, you can combine them using AND, and you can also nest them. So, for instance, you can say all the following endpoints start with /API, and then, these all are about user, etc. So I think that's really handy. So diving into the handlers, the functions from server request to server response. Notice they're all suspending functions, and we have what in Spring is called a bodybuilder function, right? But this is the coroutine version. So our find all is suspending, and with body and await, we stream the results back. So that means that the results are never all loaded in memory, and so that's one point of. I think this is really powerful because you just have flat memory use, so they're never loaded all in memory. So zooming into that that function that we have here, body and await. So this is where yeah, this didn't fit in the screen, so I condensed it a bit. So this is where basically the world of Spring coroutines is mapped onto Spring Webflux. So all the Kotlin coroutine code I showed runs on top of Webflux implementation. So the call is asynchronous, and it starts streaming bytes to the client even before all the results of the database have come in. So how do we store data and get data from persistence? So this is a repository, and let's say we count the number of users. We use a database client, so it's not using annotations. And with fetch, that's the point where we execute the query and where we get the results. And in this case, we just expect one result, and so that's what our await one suspension function does. And so this is the syntactic, so the integration between that's new in Spring Webflux. I'll dive into that a little bit further. Calling fetch will return something called a fetch spec, but basically that's the interface of tabular results, and either it's one result or multiple, of course. So in Webflux, one result is a mono, and multiple results, a stream of them is a flux. So that sounds familiar from Webflux, right? And this is the equivalent in suspending functions. So for, of course, whether it's one result or none, we can express in our types. So thank you, Kotlin. If we have multiple results, it will be a flow, like a stream of results. So the takeaway is a mono of t is the equivalent of a suspending function that returns a t, and a flux of t is a probably suspending function that returns a flow of t. But so, potato, potato, why should we care, right? Because it's a different way of doing the same thing. Well, let's have a look at some application code. So, in this example, we create a table, then we, if it doesn't exist, but, on the second startup of our application, it happens to exist, so we delete all the entries, and we insert some users. So these are all methods in the Spring Reactor implementation Java API that they all return mono or void. So that's their version of asynchronous processing, and we need to combine them all into one big mono result. Does that make sense? It's really like Rx, right? So it's not that hard to do, but it's crafted around the logic that I care about, and so if we do the same thing in coroutines, it's this. So it's a suspending function, and all the methods we're calling are suspending. And the whole need to combine it all into one value has disappeared. So I find this really cool, a really big advantage. So I've been mentioning thread locals and transactions, and yeah, how will that work, right? If our code is constantly, yeah, we basically don't know whether it will run on one thread at all. So if you're using the Java API with Reactor, you can just add a transactional annotation. So this is a feature that's really recent. So basically you have reactive transactions here. And how that works is that through all the monos or fluxes, a context is propagated. So, you know, I can't give a talk on Spring and not use one annotation. So this is the one annotation in my presentation. But you know, let's think of the code within that delete all method. You know, how does it know that the transaction is active? Well, through the reactor context. So this is how a reactor context works. We have some dummy flux that we create. And we can say that the subscriber context, we want to add, let's say, what's the word? Authenticated user in, right? And so how that works is that this is propagate. Yeah, I'm showing the function later on. So I don't know, for me it was, when I read, you know, the context is propagated upstream, I thought upstream, why not downstream? But basically the values coming downstream is basically approximately the equivalent of return value of a call. And upstream is basically the direction of your call in conventional code. And that's why the reactor context moves upstream. Does that make sense? So in, you know, well, you guys have worked with RxJS, right? RxJava, etc. Oh yeah, and the context is only propagated at the subscribe and only once, not with every value or something like that. Yeah, so how do this shows how to start a transaction. We don't use an annotation, that's not supported yet. I'm not sure whether it will come, but we have this wraparound method. So on a transaction operator we call execute and wait, and the block that we hand it to it is a suspending anonymous function that has a transaction in scope, and so and it will have a transaction context. This is propagated through the reactor context. So in the suspending function, we always have a coroutine context, right? That's the equivalent of a thread local in coroutines. In that, we can look up the reactor context because we're running within reactor, and from that we can get the transaction context. Okay, almost done. So this is what a non-blocking HTTP API looks like in the new Spring Boot. This is how you do your request processing, all suspending functions. This is what your persistence looks like. And yeah, it's I think it's a great combination. Personally, I feel that with Kotlin coroutines, there's no, what's the word? There's no longer a reason to not use async, non-blocking application, only when you really need it. So because it was, yeah, quite a bit of hassle and overhead, and I think that overhead and hassle has disappeared. So that's it.